It's been quite an interesting semester and quite an interesting year, considering this is now my third semester as an assistant professor. So before I dive in, I just want to do some quick acknowledgements. Science is not done in a vacuum unless it's actually being done in vacuum. And all of the work that I'm going to present today involves many years and many, many people who have helped out in varying capacities. A special shout out to Ben Reinhardt at 12 BMB at Argonne National Lab, the Advanced Photon Source. He's actually running some new samples for me right now, thanks to the mail-in program. And then another special shout out to my research group. The physics department at James Madison University is all undergraduate, so all these young people are all undergrad, and particularly Zach Kennedy and Dan Rossi, who have spent countless hours so far mulling through some old XAFS data as they get trained up on how to analyze XAFS. Okay, so my talk today is going to be in 3 sections. My first section, I'll just give an introduction based on the traditional concepts of materials development, and I'll introduce the idea of entropy-stabilized oxides and entropic stabilization. And then from there, I'll dive into how we used EXAFS to understand the local structure of these novel complex oxides, and then a little bit about the structure property effects on thermal conductivity, which we again used EXAFS to kind of confirm a hypothesis that we figured out through modeling. So in terms of traditional development methodology for materials, everything we work with in the modern world was actually predicted about 100 years ago in terms of its chemical and structural stability. And the way we operate is through the realm of traditional crystal chemistry, where the work of Pauling in his ionic structures, Goldschmidt in ionic substitution, and Hume Rothery in his solid solubility rules have dictated how we create our systems. And based on those rules, the general modus operandi is to identify a practical chemical structure, characterize these structure property relationships, and then modify whatever it is we need to modify for property optimization and or hybridization. Thermodynamically speaking, all of these systems are in equilibrium based on a minimization of their free energy, the Gibbs free energy G, which mathematically is equal to the enthalpy of the system minus the temperature entropy term. Now, in all of the cases of these stable materials, we see that the term that drives the Gibbs free energy to a minimum limit is going to be this enthalpy of formation or enthalpy of mixing. And with some contribution, but not a major contribution from the entropic term. And the example I have here from the thermochemical tables is for alpha phase alumina. If I pull my little excerpt here, we can see that the enthalpy of formation is very, very large and negative. And while the entropy term does increase with temperature, the product of this value still does not match what is happening here, okay? So that kind of begs the question about how does entropy really play a role in the stabilization of materials? And it certainly does. There's no argument there. There's plenty of evidence out there that suggests that we have naturally occurring entropy-assisted stabilization, such as order-disorder transitions in alloys, including beta brass and iron aluminum. And then, of course, we have studies of cation distributions in spinels or even equilibrium point defect systems. But with that in mind, we kind of ask the question, can we use explicitly entropy stabilization as a means of materials engineering? Well, people have tried this, or people have thought about it. And the first thing that comes to mind is high entropy alloys. And high entropy alloys basically became a thing when scientists, particularly, I believe his first name is Brian Cantor, started looking at the central part of a higher order phase diagram. And he found this alloy, iron, chromium, manganese, nickel, cobalt. And the general idea was if we have this 5-component metallic system and equimolar amounts or roughly equimolar amounts of each component, we're going to form a solid solution. So the idea is if S is the dominating term in minimizing the free energy, we form this solid solution. That's great. But if delta H is the dominating term in minimizing the free energy, we end up with some intermetallic. And these systems certainly exhibit very high entropy, and they have certainly interesting properties. Oh, I lost my, there it is. But there's been no real proof of entropic stabilization. Now, for example, here's an EDS map of Cantor's alloy. And while X-ray diffraction shows a single phase, the image shows chemical segregation. So it leads to a lot more questions on the role of entropy and enthalpy in minimizing the free energy. So let's begin thinking about this in a more generalized way. Let's consider a 5-component system that'll chemically react, A, B, C, D, E, okay? There's 2 generic outcomes that can form, okay? The first is that the system minimizes G through the enthalpies of formation of multiple intermediate compounds, okay? The driving forces in this case are going to be H, okay? It doesn't matter if we heat up the system to expedite kinetic processes or let it sit for an infinite amount of time, the ultimate phase will still be that of the preferred intermediate compound. In which case, the number of possible combinations or arrangements of the atoms in the system is forced to a lower number. The alternative scenario is that the system goes into a random solid solution. In this case, the driving term is going to be the fact that we have many, many possible microstates under the same macrostate. So the delta S term actually drives this reaction. So using just that basic thought in mind, we asked the question, can we stabilize a system through configurational entropy? With that, we synthesized a 5-component equimolar oxide composition. Okay, we call it J14, so I'll be referencing it as J14 basically for the rest of the talk. And it contains equal amounts of magnesium, nickel, copper, cobalt, and zinc binary oxides. Okay, using this as kind of our test subject. Okay, we came up with basically 4 criteria through a series of thought experiments that we experimentally tested to determine whether or not this system is in fact truly entropy stabilized. So the next couple slides, I'm going to explain the process of proving that this particular composition was entropy stabilized. The first is reversibility. So the transition from a multi-phase system to a single phase should be reversible with temperature, meaning that there should be an entropy stabilized regime at high temperatures, and then whatever intermediate compound would form at low temperatures proves to exist. So we took our 5 binary oxides and we started at 750 degrees Celsius. And what I'm showing you is an offset log intensity of X-ray diffractograms as a function of 2 theta. Ignore the numbers, just look at the peaks. So at 750 C, we have rock salts, spinels, tennerites, all kinds of different phases happening with our system. As we increase the temperature, we can see that the secondary phases collapse into what we consider a single phase rock salt structure at about 1000 degrees Celsius. Once we figured that out, we just lowered the temperature back to 750, and we can see that a secondary phase precipitates out of our rock salt, which happens to be a tennerite, okay? So basically copper oxide based. So we can see, there it is, that the multi-phase to single phase transformation is in fact reversible with temperature. The second criteria we thought about was a systematic component elimination. So removing a component should destabilize the solution. So up here is our single phase rock salt structure. And at this time, I believe this sample was done at about 900 Celsius, because simultaneous to us doing these experiments, we're also trying to hone in on what this transition temperature might in fact be. And then the following diffractograms are what happens when we pull an individual component out of our 5-oxide system. And we can see from this that removing any one of the components destabilizes the solution. And what's interesting is that this even occurs in the situation of zinc oxide and copper oxide. And for those of you who are familiar with ceramic systems and the Hume-Rothery rules of solid solubility, zinc oxide is a Wurtzite structure, it's hexagonal, and copper oxide is tenorite, which is monoclinic. So there's already going to be some limited solubility of these materials into a rock salt structure, and that's usually far below 20%. So the fact that we pulled an additional structure out of the system, you would think through a rule of mixtures that having more weight on a rock salt side would still stabilize the solution, and in fact it doesn't. So the next one is a little bit more complicated than just removing one particular system. This one was the minimum transition temperature to single phase should occur at maximum configurations. What do I mean by that? Well, at equilibrium, okay, delta G is 0, but G is at a minimum, okay? And we of course know from Boltzmann's equation what entropy is. And under equilibrium conditions, the temperature at which we go to single phase is inversely proportional to the entropy, which is of course inversely proportional to the number of microstates available to us. The maximum number of microstates occurs when we have equimolar amounts of each of the cations in the system. And in a 5-component system, that's going to be 0.2. So if I change my composition of one of the components, then the transition temperature at which I go to single phase should hypothetically increase. So here's what I'm looking for. I've got my log omega as a function of composition and my transition temperature as a function of composition. And here's my maximum configurations, minimum transition temperature. What I'm looking for experimentally is something like this. If I deviate from omega, I should increase T, okay? Here's the results. Up here, just for reference, my log omega with my maximum occurring at 0.2. And then here's my experimental system. So what I've done is I've systematically eliminated some part of each individual component plus or minus 10% off their equimolar values. And we can see that anytime I deviate from equimolar amounts, the transition temperature increases around some local minimum or global minimum, depends, under some minimum that of course happens at equimolar systems. The last experiment that we did was the transition should be endothermic, and an endothermic reaction corresponds to a positive enthalpy. So if the transition is in fact endothermic, then it would have to be entropy stabilized. So here I've got two things going on because we did two simultaneous experiments. The first here is basically an intensity map of temperature-dependent X-ray diffraction. So I've got temperature on the y-axis, 2 theta on the x, and then the intensity corresponds to the peak intensity. We can see that up until a certain point, we have several phases. We've got our typical rock salt, we've got tenorite, and we've got a spinel. And then as we increase the temperature, we lose our intensities until all of these peaks collapse into the 111 rock salt peak. Compared to that, we did differential scanning calorimetry. And what we found is that there's an endothermic transition right at the point where we go to a single phase rock salt structure. So through our 4 thought experiment criteria and how we experimentally showed it, we can say with some level of confidence that this system is actually entropically stabilized. But there's one point that I've completely missed, that I have not even brought up, and that was the fact of how are the cations actually ordered or disordered within the structure. I did not show you yet that this was in fact a solid solution. I just assumed it was. But through atomic resolution STEM EDS, done by my colleagues at NC State, we can see that there's really no evidence of elemental clustering in the system. So that's kind of the story behind entropy-stabilized oxides. And before I get into understanding the local structure using XFs, I'd like to pause for a second and answer any questions.
That's really interesting, Tina. I've got a question for you. So in everything you've been doing, there's been kind of an implicit assumption of a truly bulk-like phase. What about thin films or nanophases where the surface energies are different? Has there been any work on entropy stabilizing these kinds of disordered alloys in reduced dimension?
Well, as a matter of fact, most of these things that we work with are in fact thin films. As for nanoscale, like on the orders of 10 nanometers or less, I am not aware of any work on that yet, but usually.
Thin, how thin?
So we're talking between 50 and 200 nanometers.
Okay, so still much, still pretty bulk-like films. Okay.
Yeah.
All right. So surface energy, and entropy on the surface is not likely a role in those. Okay. Yeah, I was curious. We have a question from TK Sham. TK, do you want to ask?
Hi. I think your talk is very interesting. I'm just curious about the color of the mixed oxide and whether or not it's luminescent. I mean, if you're excited, can you do, say, photoluminescence or things like that?
You know what? We've tried and we've never successfully got any peaks out of it. The color, yeah, the color is almost black, but it's usually a really, really dark blue.
Okay, thank you.
Matt Newville, you have a question?
Sorry, can you hear me?
Yeah.
So thanks, Christina. I love this stuff, but I always have a question for this. Thermodynamics talks about bulk properties, and you're clearly talking about where the atoms are in discrete units. So, like, in fact, if you want to talk about a non-entropy system, that diffractogram you show, or any of the diffractograms you show, are not dominated by entropy. The peaks and the atoms are in particular locations. So is there a stat mech approach that that better describes, or, maybe not where you've got, not what you've talked about so far, but where you're going? Does that make sense?
Yeah.
Like there are phases. Yes, there are phases in the phases mix, but also there are atoms, and the atoms are places, and those are not random, right?
No, right. They're limited to what we find is that they're limited to a specific, right, the cation sublattice. So based on, go ahead.
Yeah, no, anyway, that's just like a general question and to get you thinking that, like, doesn't necessarily need a real answer.
Yeah, no, like thinking about it, it's funny because I teach thermodynamics right now. And so just thinking about it, I'm like, okay, well, we could use one of the different ensembles, but really, I mean, this is something you'd really have to dive into.
Yeah, right.
Yeah.
Okay, thanks.
Yeah, sorry.
All right, great. You should continue, Tina.
Okay, all right. Let's see here. Let me make sure I still have control of what's going on. Yes, okay. All right, so now we'll talk about understanding the local structure using XFs. Now, I mentioned before that we had talked about, or we had shown through high resolution STEM and the corresponding EDS map that it appears to be a random distribution of these cations on our cation sublattice. But if you really think about TEM, we're always looking down columns of atoms. So we could always miss something. And not to mention the fact that the sample is very small and, we're always looking at a very specified area. So one of the techniques that I was interested in using to explore further questions about not only homogeneity, but also what happens when we put so many cations together and how they interact, or how they distort on a local length scale can kind of provide us some information on the properties. So the technique, EXAFS, we all know what that is. Everyone here is probably more of an expert in it than I am. So here's the obligatory EXAFS slide. The way EXAFS work is we've got incoming X-rays that basically scan in energy space. And when we hit an energy that goes into resonance with a particular atom, we can emit a photoelectron from that absorbing atom. And then that photoelectron traverses its environment and then scatters with local other atoms. And if we background subtract the absorption edge from this, we end up with what we call the extended fine structure. Now, if we take the fine structure and we do a Fourier transform on the system, we can figure out some information about the local environment. So the first peak corresponds to first nearest neighbor environment, the second peak corresponds to the second nearest neighbor's environment. And if we take that transform, fit it to a theoretical model, we got some information. So in our case, we wanted to do the EXAFS of the different elements in J14 and see what further information we can pull from this. So this was done a couple years ago. Our measurements were done at APS 12BM in transmission mode, and we kind of scanned across the first row transition metal elements. So from 7,500 to 10.5 keV. And we looked explicitly at the copper, zinc, nickel, and cobalt K edges. The model we used, we assumed a single phase rock salt structure with a lattice parameter that we pulled from XRD, which is approximately 4.23 angstroms. And we made the assumption of random cation occupancy. And with that model in mind, we used the Demeter package to look at basically the first two coordination shells of the system, and then any of the multiple scattering paths that correspond to that data range. So looking at our first nearest neighbor fit, so here's our total fits for cobalt, zinc, nickel, and copper. And if we look at the first shell scattering paths, the information we got was kind of interesting. So right off the bat, we can see that copper is clearly distorted. And that's not uncommon considering Jahn-Teller distortion in copper oxide octahedra. And if we look at the cobalt, nickel, and zinc, we can only determine a single average bond length. And the reason for that was just our resolution limit. So based on the fact of how far we went out in K-space, we could only resolve above 0.18 angstroms. So we can't separate these path deviations below 0.18. Now, this kind of proposes a little bit of a problem. We can make some assumptions here where how is it that we have such a distortion in the copper oxide octahedra versus, you know, a globally cubic system? Well, we see this. It kind of indicates one of two things is going on. So either other cation octahedra are in fact distorted, which is not unusual, or the copper is somehow clustering. But within, you know, the view of our STEM EDS, we didn't see any clustering. So we came up with a working model that said we have a cubic lattice, and we basically have this assembly of distorted cation polyhedra that ultimately averages out into this beautiful cubic structure. So we're playing Tetris with octahedra. Awesome. The story's not over. We can kind of confirm this hypothesis by looking out into the second nearest neighbor shells. So here's our second shell scattering path lengths. We can see for all of them, they're approximately the same, okay? And it averages out to be about 2.99 angstroms. What the second shell scattering path, or half the scattering path is it's really 1/2 the face diagonal of our unit cell, okay? So if we just run some quick math here to determine our lattice parameter based on this, we find it to be 4.23 angstroms, which is exactly what we found with the XRD. So we're pretty confident at this point that the cation centers are arranged on a cubic sublattice, and then oxygen is somehow accommodating for these distortions. In order to kind of back that up a little bit, we reached out to our collaborators at NC State who do a lot of DFT modeling. And they came back to us and they gave us a pair distribution function analysis of the cation sublattice and the oxygen sublattice. If we look at the cation sublattice, we can see that the peaks are reasonably sharp and they exist in locations that one would expect them to be based on the lattice parameters of our unit cell system. But then let's look at oxygen. Oxygen is much broader, which means there's a larger distribution of positional distortion in the oxygen sublattice, which helps confirm our hypothesis. So our perfect ideal crystal structure that we know and love really is a little bit of a hot mess. Okay. The second thing I wanted to do with EXAFS is to kind of confirm the hypothesis that we really do have a homogeneous solid solution across all length scales. The way I did this was, we know that the second shell contains 12 cation positions, and our solution model assumes near equal amounts of each cation in the shell. So the question that was asked was, will increasing the specific cation concentrations in this second shell affect the fit quality? And if it does, will it make the fit quality worse or better? So to test that, I modified our theoretical model to introduce systematically clustering on a local and elemental basis. And as I did that, I checked for the fit. So I just ran fit after fit after fit. Here's the results. So here's my normalized R factor. 0 is going to be a good fit, 1's a poor fit for all 4 of the cations that we looked at. Now remember, we did not get to look at magnesium just due to the energy limits of the beamline, but if all 4 of them have the same trend, I would say it's a safe assumption to assume magnesium does something similar. So we can see as we increase the number of specific cation species in our second coordination shell, the fit systematically gets worse. So to summarize this, through EXAFS, we found that this local disorder exists between cation, anion, nearest neighbors, but it appears to average out by the second coordination shell. And we confirmed that by comparing the lattice parameter that we saw in EXAFS, or we derived in EXAFS, to that of which we found using X-ray diffraction. And the other thing we found was that the cation distribution does appear to be randomized across all of our limited length scales. So with that, I'll ask for questions again.
Really interesting. I have a few questions while people are typing theirs in. Thus far in the talk, you've only addressed systems that are stoichiometric with respect to the oxygen, if I understand. Am I right about that?
Yes.
Okay. Well, what does oxygen deficiency do? And is that a knob that you can easily tune?
It is not a knob I can easily tune for the rock salt structure. I know that other people have done it with perovskites and a couple other phases, but I can't speak to that very much.
I see.
When we try to change the oxygen deficiency, if we reduce the sample, it phase separates. If we over-oxidize the sample, it phase separates.
I see. Interesting. Okay.
Mm-hmm.
Another question that would have been related if you could have done oxygen deficiency, and that is, what do you know about the magnetism, either bulk magnetism or spin state for individual ions?
So that would be a question for the people who are currently working on that. So all of this work was done before that, unfortunately.
Oh, okay, so that is something that's being looked into now.
It is. It is.
Yeah, just in the context of XAS, I wondered if emission spectroscopy could be an interesting way of getting at the spin states of the individual species.
That would actually be, that is possible, particularly with copper, right?
The cobalt's easiest. I'd have to look up
cobalt.
whether there's sensitivity to the copper. Yeah.
Okay.
Neil Hyatt has a question. Neil?
Oh, thanks, Jerry. It's nice to talk, Christina. I'm enjoying it. I have a couple of questions. One is, have you tried any electron diffraction, and do you see any kind of diffuse scattering from the oxygen sublattice disorder in these materials?
We have not done I don't think we've done electron diffraction on these.
It might be interesting in some materials we've worked on previously in pyrochlores that gives you some nice kind of like interpretable perspectives on the order parameter. But I could send you a couple of papers on that might be helpful. And then my second question was, I missed the bit where you were talking about the impact on the kind of first shell coordination, but I think I understood that it remains octahedral, but is that right?
Yes.
But then I guess if the oxygen sublattice is disordered, that probably destroys the center of symmetry, and so then you switch on pre-edge transitions in the K-edge zones. Would that be right?
Yeah, so I'm not as well versed in Zanes as I am in XAFS, but it's definitely something on my infinite list of things to get into. But there is pre-edge structure in several of these.
Oh, that's interesting. Yeah, I think there are some interesting qualitative methods that Francois Fages and others have developed to kind of analyze that, as well as like calculations and stuff. But maybe I'll fire you an email after the talk. So thanks a lot.
Yeah, that would be fantastic. I'm actually interested in diving into Zanes and then eventually getting into the machine learning of that to help me analyze this stuff a lot quicker.
Oh, yeah, me too, but I don't know what I'm doing with it right now.
Right?
But it seems to solve everybody's problems.
Yeah. Thank you.
Thanks.
You should continue, Tina.
Okay. All right. So let's see. Okay, we're good. We're still good. Okay. So the next part of the talk, basically I'm kind of giving you a timeline from my PhD, and then now I'm going to step into one of the studies we did as a postdoc before I took my professor appointment. So this work was done when I became a postdoc at the University of Virginia. And our objective here was to investigate the thermal properties of our ESO composition, okay, so of J14. And then we kind of wanted to see what would happen when we added a 6-component to our 5-component solid solution. So we came up with several different elements to kind of see what our limitations were in terms of, atomic properties, and if we can kind of back out any sort of relationship between what these elements are a little bit known for versus the properties that we observe. So we chose scandium because it has a similar ionic radius, but in the octahedral state, the majority of the time it likes to sit in 3+. Chromium has many, many oxidation states. Germanium has more covalent nature. Antimony, similar to scandium, but it has a very high atomic mass. And then tin has lone pairs. And we ended up using a laser-based technique called frequency-dependent time domain thermoreflectance to back out the thermal properties of our system. So the first thing we did was come up with or figure out the volumetric heat capacity. And what we found is that it really does follow a rule of mixtures. So in the background, on the left-hand side, I've got heat capacity as a function of temperature, and I've got my 5-component system, the heat capacities in the individual, and then this purple line is basically the rule of mixtures. The scatter plot sitting on top of the purple line is what we experimentally found for the volumetric heat capacity of the J14 system, which kind of provided us with, well, yeah, okay, it follows the rule of mixtures. Really great. Now the thermal conductivity on the right-hand side versus temperature, we see some interesting things. So in the background, I've got all of the bulk models, or all of the various models of each system, we kind of started to explore. So at the top, we have the thermal conductivity of magnesium oxide, and then, you know, due to volume, we lower the thermal conductivity in a 300 nanometer thin film. Then we have a 2-component model, a 5-component model, and a 6-component model. And we see we kind of approach some asymptotic limit of the number of components. The scatter plot sitting on top of our model corresponds to the 2-component system of various systems. So we've got cobalt, nickel, zinc, magnesium, and copper, nickel, which they're not too far off of what the model says. And then we have our 5-component ESO, which is reaching a limit. And then we've got our 6-component ESO, which, if we look at as we approach room temperature, it looks like within uncertainty, it approaches the amorphous limit of magnesium oxide. So that brings up, you know, a plethora of questions as to why this is going on. And so we started to kind of explore why the thermal conductivity in the system is different. So thermal conductivity is 1/3 CV squared tau. C is the volumetric heat capacity, V is the phonon group velocity, and tau is our scattering cross section. Something to point out here is that, electrically speaking, all of these are very insulating. So we're only really dealing with the phonon thermal conductivity. If we plot the thermal conductivity as a function of atomic mass for J14 and J14 plus the 6 components, we can see that, of course, there is a decrease in thermal conductivity as a function of mass, as one would expect, because if we introduce something of a heavier mass into the lattice, we're going to scatter phonons a little bit differently. But the interesting thing here is this addition of chrome. So chrome has a very similar atomic mass to the average, right? It's kind of right in the middle of the first row transition metal elements. So that brings up the point as to what could be happening in the chrome system such that we still have this decrease in the thermal conductivity. And to do this, Jeff Braun, who was a grad student at the time, his specialty is absolutely thermal properties. He used the virtual crystal analysis method. So he built a model to try and tease out what possible effects could be having. So in the background, we've got purple and gray lines, which you know, depict the virtual crystal approximation without fitting parameters for our 2-component systems. And then this maroon line at the bottom is the minimum thermal conductivity for amorphous J14. Okay, and then of course, the shaded regions correspond to uncertainties. The temperature independent nature of this, if we really look at it, it's basically a flat line. The nature of the mechanism causing this reduction kind of suggests strong Rayleigh scattering as opposed to Umklapp or any of the other mechanisms. So at first, the VCA model didn't exactly work, but the addition of another order parameter that kind of compensated for what we consider the interatomic force constants based on changes in cation oxidation state helped us match this model a lot better. And what we found was that the best fit VCA models revealed that this interatomic force constant disorder scattering leads to this level of reduction. So it led to the hypothesis that it froze. Are we good? We're good. Okay, sweet. So we ended up hypothesizing that this IFC disorder introduced by the local ionic charge disorder is what's actually changing the thermal conductivity. And if this mechanism is really there, we should be able to actually probe the local structure and see if adding a sixth component changes any of the local environment of any of the host atoms. So to kind of give you a takeaway, because that whole thing really is like, it is a paper of its own. To give you a takeaway on this, right, if we change the charge of a particular cation, it changes the underlying potential of the nucleus and the surrounding electrons. So depending on whether we add an electron or take away an electron, we're changing the ionic radius of this atom, okay? When we change the ionic radius, the structure then has to compensate on a local level. It finds a new equilibrium, so it distorts based on this modified ionic radius. And this local distortion ultimately modifies the scattering term in the thermal conductivity. So to test that out, we go back to our friend EXAFS. So here I'm showing you the fit of the first technically 3 coordination shells, but it's really 2, of J14 on magnesium oxide. So this is about 150 nanometer thin film, and we're looking at the cobalt absorber. And what we see is that the lattice parameters we know from XRD were pinned in plane, so we're matching the MgO lattice parameter of 4.21 angstroms, and the out of plane lattice parameter is 4.29 angstroms. So we're basically extended out of plane a little bit. The first path, here are the ideal calculations based on the model and the unit cell lattice parameters. Here's what the model tells us. And within uncertainty, it's exactly what we would think it would be, okay, given the constraints of the thin film on the substrate. Now, if we go to J14 plus chrome, it's a little bit of a different story. So we're still pinned in plane, but now we're compressed out of plane with a lattice parameter of 4.08 angstroms. And if we look at the ideal half scattering paths that we should expect based on the unit cell parameters, as compared to what we found when we fit our Fourier transform, we see that there's a difference of about 6%. So the fact that we introduced chrome into the system has kind of changed the entire landscape, okay? And the example that I show here is how cobalt responds to the chrome. But I have other data elsewhere that kind of shows that they all respond in very different ways to what the sixth element might be. So to summarize this, higher disorder reduces thermal conductivity. That's not new, right? You know, someone called the press. But the degree to which this reduction occurs is beyond the predictions of any of our analytical models when a sixth component is added to this host. And based on VCA, we see that these distortions are due to the local potential fields based on charge compensation for electroneutrality, and that's much, much greater than any mass disorder introduction. So to wrap up, we know that configurational disorder can in fact promote reversible transformations between a multi-phase and a single-phase solid solution of 5 or more binary oxides. And this really provides unique opportunities to explore some novel structure property relationships. And this slide's a little bit old, it's kind of dated. There's been some more stuff that has come out, but they found some interesting properties like colossal dielectric constants, room temperature, superionic conductivity, even in application for water splitting. And this was the Majumdar group at Stanford, I believe. So with that, I am happy to take any more questions.
Terrific talk. While people are putting their questions into the chat, I guess I have a few. You mentioned superionic conductivity, and I usually think of that in the context of oxygen deficiency, which brings back my question again. Is it actually impossible to get oxygen deficiency, or just hard, or am I misinterpreting the superionic conductivity here?
So I believe in this case, it's hard to do. I think there is a limit of how much deficiency we can have before we lose that structure stability.
I see. Okay. All right. Very good.
Mhm.
Another question is echoing Neil. Boy, I'd really love to see how the Zanes changes on the cobalt for exactly the 2 samples that you were describing.
Oh, yeah. I actually have that data. I just have never had a chance to really dive into it. So I can do that.
Yeah, we'd just be curious about the pre-edge features.
Sure.
A question from Matt Newell.
Yeah, hi, Christina. Yeah, very nice. When you presented the XAFS results, you showed that the distance contracts pretty substantially. Do you see asymmetry, or did you look for a third cumulant in a more in those distances?
I did not.
Aha.
So
Because it's sort of well known that for highly disordered systems, and these might be, that a third cumulant can be important and often skews towards lower, or without not including it, skews towards lower distances.
interesting.
So
Okay.
it's worth looking into.
Yes, absolutely. Thank you.
Thanks.
All right, a last question, a bit open-ended. Where are you going next with these systems?
Oh wow. Okay. So currently we've got funded for an NSF MRSEC with my previous PhD advisor at Penn State and the University of Michigan. And now we're starting to explore some more complex thin film structures like pyrochlores, fluorite structures, things of that nature, and more elements up to 10 plus cations in a system to try and determine not only to bring up like a structure property database for something this complex, but to also kind of understand what it really means to be entropically stabilized and how we can exploit that and tune structure property relationships based on entropy stabilization. So the goal is a little bit, not by a little bit, it's very, very broad, but my role in this is to really hone in on XAFS and learn Zanes and be able to help model these structures better and try and relate local structure to the properties. So that's kind of where we're going with it right now. But this is such a new thing that the possibilities really are endless.